Welcome to lecture. We'll get started in just a second. Continuing on chapter 14, I think. And again, if you have questions, feel free to ask them. And we'll get started in just a second or so. Okay, so when we last left off, we were talking about acids and bases here. And we're talking about the pH scale, the pOH scale, how to calculate H plus, and all that good stuff. So just to run through again a review that basically a lot of times we talk about the Bronsted-Lowry definition of an acid and base. Again, an acid being a proton donor, a base being a proton acceptor. We also talked about Kw, which is the H plus concentration times the OH minus concentration. And again, at 25 degrees, that does equal 1 times 10 to the minus 14. The relationship between H plus and OH minus is a opposite relationship, which means basically as one goes up, the other goes down, and vice versa. So they basically kind of move together but in opposite directions. We also talked about the pH scale. Again, that runs from 0 to 7 to 14, below 7 being acidic, above 7 being basic. Again, right on 7, as we talked about, being neutral, because at that point where these guys equal each other, under normal conditions, that means that they both would equal 1 times 10 to the minus 7, which if you then put into our pH equation that we also saw, would technically give you a pH of 7 in that case, which is basically what neutral would be. So this is how we do calculate the pH, as we talked about as well. We could also calculate one that looks at OH minus, the amount of free OH minus in the solution, and that's minus the log of the OH minus. And again, the benefit of that is the relationship that you could take the pH plus the pOH, and that will equal 14. So that gives you a little bit of sort of a variety of ways that you can solve these type of problems. We also saw that if you have the pH, you could get the H plus concentration from it, and that's the inverse log of the minus pH. Again, on most people's calculators, when you do the inverse log, that's when it will pop up that 10 and a caret, and you want to take the minus pH. You could also do that for the pOH as well, except that the pOH, much like the name implies, will not give you the H plus concentration, will give you the OH minus concentration. Pretty much the exact same calculation, the inverse log of the minus pOH. And that's going to get you a 10 to the minus pOH on top when you do that. So by using all of these guys here, you have a wide variety of ways that you can solve for H plus concentration, OH minus concentration, the pH, the pOH. A couple other things that we talked about again is when you're trying to determine whether a solution is acidic, basic, or neutral, you should always really look at the pH scale, which is the one on the top there. And that is because that's usually the scale most people have in their head. The pOH scale, again, runs opposite. So if you have a high pH, you have a low pOH, and vice versa. If you have a low pH, you would have a high pOH. So because most people have the pH scale in their head, that's the one you should always look at in terms of determining if a solution is acidic, basic, or neutral. And I think, as I mentioned last time as well, the answer can't be like all three of those things or even two of those things. So the solution can't be acidic and basic at the same time. And again, that's a very common answer sometimes people will give because they look at the pH value, like I mentioned last time, and go, oh, it's above 7, so it's basic. But then they look at the pOH value and it's below 7 and go, oh, it's acidic. And they end up giving kind of two answers for that question. So don't do that unless you want a big X. So you can just put an X yourself on it if you decide to do that. But make sure you just choose one of those. Any questions on any of that stuff that we sort of talked about, I think, at the beginning part of this chapter? And what we sort of finished on was the idea that, you may not always be given sort of a generic H plus or H3O plus concentration or OH minus concentration. You may be actually given a formula for an acid. And one type of formula that you may be given is a formula of a strong acid, which is sort of where we left off. And if you're given something like HCl, which is a strong acid, it is going to 100% break apart into H plus and Cl minus. And what that means is essentially you do need to figure out what just the H plus concentration is if you're trying to figure out the pH of it. In this case, it is a 1-to-1 relationship, since something like HCl is what is known as a monoprotic acid. Monoprotic acid basically means that the acid can donate one H plus. There's also diprotic acids, which has a general formula of like H2A. By the way, HA is the generic formula for a monoprotic acid. So something like H2SO4, which is sulfuric acid, actually has two H pluses that can come off. And there's also triprotic acids, are sometimes referred to as polyprotic. And that is something where they can give away, obviously, 3 H pluses. And that's a generic formula for a triprotic acid. And something like phosphoric acid, H3PO4, is a triprotic acid. The other thing that we talked about in terms of that as well is they do come off one at a time. So when we have our diprotic acid or triprotic acid, although they do technically drop off 2 H pluses, for example, for sulfuric acid, it does come off one at a time, which is something we also talked about last time. Again, what's going to first happen is our H2SO4 will drop off that first H plus and make this. Our next one, our HSO4 minus, will then drop off the second H plus and make our sulfate. So as we were talking about with acid conjugate base pairs, that is why this guy and this guy is pair, and that's why this guy and this one is a pair. But again, going from H2SO4 directly to SO4 2 minus, they are not pairs because they really aren't related to each other because they're pretty much 2 steps down the way. Although a lot of times why we always kind of think about it as they just come off together is if you add both of these reactions together, this cancels and you're left with what you normally kind of think about when you look at sulfuric acid is this overall reaction of you get your 2 H pluses and your SO4 2 minus, as I run out of room on the bottom there. So sometimes that's why we sort of think about sulfuric acid or something like that as oh, I've always sort of seen this equation here, you know, as sort of the overall equation, which it is, but it is made up basically of two steps that occur kind of individually beforehand. And again, that's why those things are not partners as you go from the H2SO4 to the SO4 minus, because it's actually, as you can see there, two-step process. Any questions on any of that stuff that we talked about there? So remember as well, though, that if you are dealing with a strong acid or a strong base, you are going to have to figure out the H plus concentration for your strong acid, your OH minus concentration for your strong base. And this table here is a list of some of the strong acids and strong bases that we kind of commonly come across. So those guys on the left there, we talked about last time as well. So perchloric acid, hydrochloric acid, hydrobromic acid, hydriodic acid, nitric, and sulfuric acid. These are all examples of strong acids, which means they're strong electrolytes, which means in solution, you have none of those units still together. They have 100% broken apart into H plus and whatever their anion is. And that again is why they're considered a strong acid, because pretty much when they go for a swim, you know, they produce a lot of free H plus. And it's that free H plus that really makes the solution acidic. The greater amount of H plus that you have that is free and floating around in that solution, the lower the pH would be. And on the right is some of our strong bases. And as we talked about last time as well, our strong bases typically will have hydroxide actually in the formula. And that's what we see here: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium, and barium hydroxide. Again, pretty much our strong bases come from group 1 and group 2 on the periodic table. Again, they're called alkali metals and alkaline earth metals. And pretty much what alkaline means is basic. Yeah, so alkaline means, let's write basic. Means basic. So a lot of our really kind of strong bases come from group 1 and 2 that has hydroxide in it. And they also, when they are in solution, will 100% break apart, as they are these strong electrolytes. And that means that in the solution, you pretty much have 100%, for example, sodium ions floating around. And more importantly, in terms of pH and acidity, you have 100% OH minus ions that are flowing around. And again, because you generated a lot of OH minus very quickly, because OH minus again is related to H plus. So by doing so, when you increase that OH minus concentration, that H plus concentration is going to go down. And once that H plus concentration goes down, the pH will then go up into the basic range. So these are strong bases again, because they generate a lot of free OH minus very quickly. Any questions on that there? And the last thing I think is, again, something like this. The guys here, when they do break apart, remember they don't break apart into a one-to-one relationship. So when this guy breaks apart, you get a calcium ion, plus you get 2 hydroxide ions, which means if this guy was 2 molar altogether, the hydroxide would be 2 times 2 molar and would be 4 molar in that made up example. So you would have to double the concentration of hydroxide to get the correct one. Once you do get the hydroxide concentration, you would then want to obviously go into the POH, subtract 14, and that would get you to the pH. So again, a reminder, if you do have questions, feel free to type them. Even if I move past, I will come back and get to it. So that's how we deal with strong acids. When we deal with weak acids, it is a slightly different calculation. Because it's a weak acid, we will get basically this reaction here, and we will get that reversible reaction. And if you remember, that reversible reaction means that it will eventually reach chemical equilibrium. And that means that the rate of that forward reaction will equal the rate of the reverse reaction. And that means that we could write our good friend, what is known as Ka, which is really just an equilibrium constant. So adding to our ever-growing list of K values, we've seen Kc, we've seen Kp, we've seen Kw. Ka, much like you might expect, is an equilibrium constant for a weak acid. So when we have a weak acid and we want to figure out how what the pH is of that solution, it is actually a different type of calculation. You cannot go directly into the pH equation with these guys. So when you have a weak acid, unfortunately, unlike a strong acid, you cannot go directly into that. And since it's an equilibrium constant, it's a reversible reaction, you might as figured it out. That means we're going to have to do our other favorite thing, which is ice tables to solve these guys. So weak acids and weak base problems are very different than strong acids or strong bases in terms of trying to determine the pH of the solution. You pretty much have to do an ice table. And the only difference is in the equilibrium chapter, we were essentially interested in the concentrations of everybody at equilibrium. When you do this, usually with a weak acid or later with a weak base, but definitely with a weak acid, really the only thing you're interested in is sort of at the end, the concentration of your H plus. And that is because once you determine your concentration of H plus, you will then be able to actually then go in to your pH equation. So before we can go into our pH equation, we will have to do an ice table. The purpose really of that ice table in most cases is to figure out the equilibrium concentration of H plus. That will tell you basically how much free H plus is floating around in that solution. Once you figure that out by doing the ice table through the same method as we did in the previous chapter, you then would have the ability to go into the pH equation and actually figure out what the pH of that solution is. Now, as the Ka value increases, so does the strength of the weak acid. And what this relationship is the same thing we talked about with the equilibrium constant. When we have a large value of K, that means when we reach equilibrium, we mainly have products. And vice versa, like we talked about before, if we have a small value of K, what that means is it mainly has reactants. And remember, regardless of the K we're talking about, if it's Kc, Kp, Ka, Kb, Ksp, all the Ks we're going to learn throughout the rest of the semester, they're all essentially the same thing. They're all equilibrium constants. So it really doesn't matter. You can mix and match them. And in this case, because the Ka value would be large, that means that we would mainly have our products. And on the product side, that is where we see our H plus, which means we would be producing a lot more H plus, and thus it would be a stronger weak acid. So just to be clear, that means it's a strong weak acid. It is still a weak acid, which by definition means it's a weaker acid than something like hydrochloric acid, hydrobromic acid. It is much, much weaker than that. And vice versa, if your Ka value was a small Ka value, that means that your weak acid strength would go down. And for the same reason, if you had a small value of K, that means when you reach equilibrium, you mainly have the entire acid still together, which by definition would mean you did not produce a lot of free H plus. And thus, if you did not produce a lot of free H plus, you then would have a higher pH, right? Not as much of it wouldn't be as acidic in that case, and it would be a much weaker weak acid. So when we're talking about sort of the strength of an acid based on Ka values, it is only within really the realm of, not pushing the button, only in the realm of here, weak comparing weak acids to other weak acids. So again, a weak acid would be obviously a lot weak than any strong acid. Any questions on that there? Okay, so this is a table from your book. And again, it gives you a lot of these weak acids. So acetic acid is a common one, hydrofluoric acid, carbonic acid. And it also gives you the Ka values for these guys. You will also see this guy right here, which is carbonic acid, is a diprotic acid. So it actually gives you two K values. One's a Ka1, one's a Ka2, and that is because it's diprotic, much like sulfuric acid. The first thing that's going to happen is this guy is going to drop off its first hydrogen, and that would be Ka1, which from this table is 4.3 times 10 to the minus 7. Then the next thing that would happen is this guy would then lose its next H plus to get us to carbonate, and that would be your Ka2 value for that reaction that is occurring. Just like normal, when we talked about our K values, they are specific for the reaction as to how it is written. So obviously it is specific for, that 4.7 number is specific for that second hydrogen coming off. So that's why we see two values there, one for the first hydrogen coming off and one for the second. Our sort of monoprotic guys will give you, just one answer. Sometimes these other ones are extremely small, so they might not even give you them in these tables. You could find them in other tables. Here's some more weak acids. And again, in problems, you may have to consult a table or this table to answer the questions. A lot of times they will give you sort of the K value in the problem, but sometimes they may not. So you may have to obviously look it up in a table. On an exam or quiz, it would obviously be provided to you either in the problem or you would be provided this table where you can go and look it up. So I think there was sort of a question the other day as well as to how do you know if it's maybe a strong acid or a weak acid? And this is a big way to know that if you have any type of Ka value that's associated with an acid, either in the problem, which a lot of times it is given to you in the problem, or again, if you look it up on the table, that is a pretty good tell that it is going to be a weak acid. So that's a good way to know for sure that you're dealing with a weak acid. If you're given a formula for an acid and you can't find that acid on the table, you would probably be sure that it's a strong acid. And again, those kind of 7 strong acids that we saw earlier are probably the common ones. So the question is, will a strong acid have a Ka value? So will a strong acid have a Ka value? And really the answer to that is no, it will not have a Ka value. And the reason a strong acid will not have a Ka value is a very simple idea. If you take something like our hydrochloric acid, it's going to 100% break apart in solution into our H plus and our Cl minus. And again, in that solution, that is what you have, 100% of this. Remember, in order for you to have an equilibrium constant, you need to have a reversible reaction, which means you need to have some reactants, you need to have some products there. And in a equilibrium situation where you would have a Ka value, it's a two-way street. There's stuff heading in both directions. Remember, in a strong acid, I'll make this bigger, it is a one-way street. Yeah, there is nobody coming back this way towards our reactants, and thus it cannot set up an equilibrium. So if it cannot set up an equilibrium, you cannot have an equilibrium constant. And if you can't have an equilibrium constant, then you can't have a Ka value. So that is why when you look on these tables, you typically will not see a strong acid on it. The only one that you sometimes will see on it is like H2SO4. And that's for the first step where this guy drops off that one H plus. And in a lot of tables, they simply put the value of it's very large, which is obviously not very helpful for calculations or anything like that. But you will see the second step, which is over here on tables and stuff like that. So that's probably the only sort of technically strong acid that you will see, maybe appear on the table, Ka table, that's kind of technically a strong acid, but usually there's not a number associated with it. It's something that just says large. Any questions on that? Okay. That's a big table in your book. It just kept going. All right. So why don't we try one here? So I tell you what, why don't you give it a try? Take a few minutes here, take maybe 5 minutes or so, and try to calculate the pH of the solution. Again, I'll give you a hint if you can't see it already. This right here should be your hint that this is a weak acid. And what you want to do basically is calculate the pH. So you are going to have to do an ice table. So I'll give you a few minutes. Why don't you at least get started on the ice table here? Again, it's done the exact same way as all the ice tables that we did before. You need the equation. You have the initial concentration. The goal here is to ultimately find the H plus concentration. So why don't you take a few moments, start working through it, and then we'll talk about it in a few, see how everybody's doing. And again, if you do have questions, feel free to ask them. Okay, so you've had a little bit here just to get started on it. So let's just walk through it here. So make sure everybody's approaching it the same way. Again, as I mentioned, the way we could recognize HF, if we didn't know it was a weak acid, again, that Ka value is a big telling sign that it is a weak acid. So again, that automatically means that you do need to do some type of ice table problem like we did in the previous chapter. So we'll take our acid here and we're going to dissociate it. And again, here I'm going to leave out the water and just break it apart into H plus and F minus, which a lot of times when you start doing ice tables, it's probably a little bit better and easier. So you don't try to use the water. Again, you could do the equation like we've seen previously with the water, if you like. And you'll get your H3O plus and your F minus in this case. And again, the reason why sometimes people will leave it out when they're sort of doing these weak acid problems and ice tables is, if you remember, when we do our K, we don't include liquids like water. So essentially, it's usually left out anyways. It's not going to be part of the calculation or anything like that. So sometimes, like I said, most people a lot of times will leave out the water, especially with the acids, because it's not really going to participate much in the calculation or anything like that. But if you want to leave it in, you can. Just make sure you don't include it in any of the calculations that you do. So initially here, the only number we're given is 0.5 molar. Again, just like in our equilibrium ones, we could then safely assume that we have 0 of these guys. This also should safely allow us to assume that the reaction really is heading in that direction towards our products. So our change here, just like a normal ice table, minus on this side, minus x, plus x, and plus x, which means when we get to equilibrium, we will have 0.5 minus x, x, and x. So any questions on the table? It's essentially the same table as we did kind of in the previous chapter. We're going to kind of approach it the same way. And just like in the previous chapter here, we're going to use the equilibrium expression, which if we write it for this, this would be a Ka value, again, because it's a weak acid. It's going to be our products over our reactants. And again, in this case, all the coefficients here are 1, so we don't have to worry about any of that kind of stuff. And that would equal our 7.1 times 10 to the minus 4. So just like a normal equilibrium problem, we're going to take our equilibrium line and we're going to put it into our expression. And if you do, you essentially will get x squared on top divided by 0.5 minus x equals 7.1 times 10 to the minus 4. Now, just like we did in the equilibrium chapter, when we look at this number here, this is a small number. And remember that when you're doing equilibrium problems, if you come across something that is small, you can try an assumption, right? You can assume that x is equal to 0. And that is what I'm going to do here and give it a try. And again, when you do that, it is only the x's that you're subtracting from something or you're going to add to something. So that would get us x squared on top over 0.5 equals 7.1 times 10 to the minus 4. We're going to multiply the 0.5 to the other side, and most importantly as well, make sure you take the square root of it. So 0.5 times 7.1 to the minus 4. And then when you take the square root of it, you get this answer here for x. X would equal, again, after you do all those steps, multiply and take the square root, 0.1, we'll call it 88. Now, a reminder, just like we talked about before, if you make the assumption, you do have to check your assumption. So to check your assumption, we again are going to use the 5% rule here. So we're going to use that 5% rule. So to check your assumption, you take the X value that you got, you divide it by what you're going to subtract it from, which in this case is 0.5. You times it by 100%. And if you do that, you get something like 3.7%, which means this is a good assumption. Again, it's under 5%. Any questions on that? Checking your assumption or any of that? So in this case, which is also really where these problems sort of deviate from a normal equilibrium problem, is we're not really interested in the equilibrium concentrations of everybody, which we could get by going into here, because these are all the X's, including the X on this side. But in this case, we're really only interested in the H plus concentration because we want the pH, which means that the H plus concentration equals X, which means it equals 0.188 molar. Then we could go into our pH minus the log of 0.188. And I feel like I missed a zero there somewhere. Hang on a sec. I did. My bad. I apologize. I did miss a zero. That would make it a lot better. We'll just squeeze that in. 0 and a 0 here. There we go. So it helps if you don't miss a zero, I suppose. Let's try that again. So again, X in this case is 0.011, and that gives us 0.188. This number is still right because that is what I put in. I just forgot to write the zero there. So when we do that, that then gives us the correct pH, 0.0188, which is 1.72, 1.75. If you did use that number, 1.73 looks like. Which this is an acidic pH, which also does make sense since HF is an acid. Any questions on that other than don't miss the extra zero, I suppose, when you write it? So hopefully what you can see here is that it is pretty much the same steps. If you didn't assume X is equal to 0 and you solved it through the quadratic formula, you really should still get the same answer. So I would double check your math. So you definitely can, like we talked about in the equilibrium chapter, you can go through the calculation and just go straight into the quadratic formula if you want. It should give you the same answer pretty much. With rounding, it should be pretty close to the same answer. Maybe you got 1.72 versus 1.73, but it should be pretty much the same ballpark. Again, you don't have to do the assumption. If you like the quadratic, you can go into that. You would need to probably solve it mathematically, I think, to answer your question. So either you'd have to use quadratic formula, or you would have to solve it with the assumption here. Yeah, it is a weak acid, but it doesn't necessarily mean that the pH will be a higher sort of acid. It is dependent on the concentration as to how much H plus may come off in that, and we're going to talk a little bit about that as well. Other questions on that there? All right. So just to show you as well that the concentration does affect whether or not, for example, if your assumption is good or bad, and you should check it, it is going to be this is going to be the same ice table that we did previously. If we change this to 0.05, we would have our zeros. We would have our minus x's, 0.05 minus x, x, and x. Then when we get to our table, x squared divided by 0.05 minus x equals our Ka value, which again was, where's my Ka value on that one? 7.1 to the minus 4. If we make our assumption here, this is going to give us, again, x squared over 0.05 equals 7.1 times 10 to the minus 4. And if we do this, which is essentially the same problem, the only real difference is the concentration, 0.05 times 7.1 to the minus 4, the square root. This would give us an x value of 0.00596, which then if we check this guy, 0.00596 divided by 0.05 times 100, we would get something like 11.9%, which means this assumption would be bad in this case. So you want to make sure that you do check it, because the assumption will not always work. And it has to do with concentration. So we'll talk a little bit more about this later in this chapter, but the first concentration was 0.5, while this concentration is 0.05. Although both of them are giving away a little bit of H plus, right, when it breaks apart. It's kind of like sort of the pizza example. If you have a whole pizza and you take like one piece, it's not that big deal. But if you're already starting with like only 2 pieces left in that pizza and somebody takes one slice, it's a bigger proportion of what you started with. So the change is a bigger proportion that's going to happen. So the concentration in sort of these weak acids will have an effect on whether or not, sort of that assumption will work. Again, if you started with a higher concentration of a weak acid, the little bit that comes off is going to be relatively small compared to where you started with, as opposed to if your concentration of weak acid was very small to begin with. When you lose a little bit of that in terms of H plus, it's actually going to be a bigger part of the pie, if you will, and it will usually not work in terms of the assumption. So it's a good reminder that if you do make the assumption, you should always check it, because it will not, work 100% of the time. Obviously, in this case, you would then, for our purposes, have to go back and do some quadratic formula and solve it that way. All right. So when we do these problems, as we sort of went through our last example there, we basically approach it the same way. We approach it the same way as a regular equilibrium process. We also ignore, in most cases, the contribution of water. So what that means is, and for our purposes, we will ignore it, is when we have water, as we talked about, it is constantly going back and forth, right, and generating H3O plus and OH minus, which means, technically speaking, you could have some problems where the H plus concentration or the OH minus concentration is actually a lot less than the natural H plus concentration or OH minus concentration that would be there from water. And that involves sort of multiple equilibrium, which we don't really get into here. So we usually will ignore the contribution of water in sense of the H plus or OH minus concentration that it contributes. So for example, if you had an H plus concentration from water, that was, say, 1 times 10 to the minus 6. And then you did your calculation from the acid, and it gave you an H plus concentration of like 1 times 10 to the minus 11. Some books and people will say, that's so small that really this guy here is really what's the H plus concentration from water is really what's the major H plus in that solution is, and they will just go with that. So we ignore water's contribution. We look at the acid as the acid is sort of the only one generating H plus, and like if we had a weak base as well, that the weak base would be the only thing generating the OH minus in those solutions, and we ignore any contribution from the water that's in there. So if you come across a book or something like that, and I don't think your book does it either, it ignores the water concentration in most cases, but sometimes you'll see that in books. They'll go, well, the water concentration is much larger than the acid contribution, so we ignore the acid. So for us, we're going to do the opposite, and most people do the opposite, that if you have a weak acid or weak base, they're going to be sort of the major contributors with quotes in terms of the H plus or OH minus contribution in that solution. We do an ice table just like we just did in that problem. We want to solve for X, and really in most cases, we were interested in the H plus concentration, and we want to go into the pH equation after that to calculate it. So why don't you try another one just to make sure here. And give it a try. So take a few minutes here and work through that. Again, a generic formula for a monoprotic acid, if they're not talking about a specific one, is HA. So you can use HA as your generic sort of formula. So give it a try here, see what the pH is. And again, to answer sort of an earlier question that scrolled by, you can have a low pH with a weak acid, just like a strong acid. And it does have to do with the concentration of that weak acid as to how much it may be given off. It may translate to a low pH, but is still considered a weak acid compared to a strong acid. A strong acid that maybe had the same concentration would probably even have a lower pH at that point because it would produce more H plus in that solution. So in terms of strong acid or weak acid, you can't really use pH to determine that. What the pH will just tell you is it is, relatively acidic, that solution, versus that's definitely a strong acid or a strong base. So take a few minutes and then we'll go over this calculation. All right, so let's take a look and see how we're doing. So again, whenever you're sort of not given a specific acid, more of a generic one, you can kind of use these sort of generic formulas for it. Again, we see a Ka value, so that tells us this is a weak acid, and we do need to do an ice table. So we will set up our reaction here. H plus and A minus. So we're going to do our ice table. So initially we got 0.122. We're not given any information about these guys. So we're going to assume that they are 0. We're going to do our change, which would be minus x, plus x, and plus x. Then at equilibrium here, 0.122 minus x, and whoops, get the x over there in the right spot. Any questions on the ice table? So again, looks very similar to the 1,000 ice tables you maybe have done at this point. Maybe not 1,000, but pretty close. Again, here we could write a Ka for this, which is our products. Excuse me. Over our reactants. And that's going to equal 5.7 times 10 to the minus 4. So like before, we're going to then take our equilibrium line. We're going to toss it into that equation there and see how we do. So putting it into here will give us x squared over 0.122 minus x equaling our Ka value. Again, it's a small Ka value, so we can assume x is equal to 0. And if you do that and you run through it, you should hopefully have checked it because it is bad. Yeah. So when you do that, if you do the assumption and assume x is equal to 0, and you take 0.122 times 5.7 to the minus 4 and take a little square root action of it and divide it by 0.122, you get something like 6.8%, which is above 5. So that is not good if you did take that assumption, which means you cannot do the assumption in this problem. And also important to make sure you do check it. So we do want to solve it using the quadratic here. So we're going to have to expand out everything. And if we multiply the bottom to the other side, we will end up with x squared equals 0.1, 2, 3, 4 zeros, a 695 minus 57 times 10 to the minus 4x. Bringing everybody over to the same side gets us x squared plus 5.7 times 10 to the minus 4x minus 0.0000695 equals 0. Again, this is going to go into our x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And since I'm running out of room here, hopefully you know how to do this at this point. Again, this is our A, our B, and our C. And if you do that, I believe you kind of put the numbers in, you get minus 5.7 times 10 to the minus 4 plus or minus, when you take care of the square root part, you end up with 0.0167 divided by 2, which gives you an x value of 0.00806 or minus 0.00863 in that case. Just like before, when you do get these two values, one will not make sense. And hopefully, you know, in this case, it is the negative one that should not make sense because we are looking for the H plus concentration, and that is equal to X. So that means that our X value, which equals our H plus, is equal to 0.00806 molar, which means our pH would equal minus the log of 0.00806. And that would get us a pH in this case of 2.09, give or take. Any questions on any of those steps? Now, I'll be honest with you, in this particular case, because the percentage was only 6.8%, if you did the assumption and you got the pH, yeah, you got a pH pretty close to that number, I think. Maybe like a 2.07, maybe even 2.8. I don't recall off the top of my head. You did actually get a number that was fairly close to what we got here. For our purposes, again, we're going to stick with that 5% rule. So you would technically need to go through the quadratic formula here to solve it. It would be incorrect. It won't always turn out that way, that the assumption and the quadratic will come out, you know, pretty close to each other. Again, especially if you get into sort of a higher percentage above 5, but sometimes they will come out close to each other. But you should still follow the 5% rule and solve it the way we just did here with the quadratic. Any questions on that there? All right. So why don't you try this one here, see what you come up with. We've got some options there. We're looking for the H plus concentration in this case for a 0.01 molar solution of HCN, hydrocyanic acid, Ka value 6.2 times 10 to the minus 10. Take a couple of minutes here and see what you come up with. Okay, so let's take a look at this one. Again, the hint here is we do have a Ka value, so we know it is weak. So if we do run through our ice table, we're going to take our acid. It's going to dissociate into H plus and Cn minus. Again, we're given our initial concentration of 0.01 molar. We can assume we have 0 of these guys. We're going to do a minus X, a plus X, and a plus X, which means we will end up with 0.01 minus X, X, and X. Again, we could write a Ka expression for this, which is going to be our H plus times our Cn minus divided by our HCN. And this would equal 6.2 times 10 to the minus 10. Putting in our values here, we will get x squared divided by 0.01 minus x equals our 6.2 times 10 to the minus 10. Any questions up until that point? Again, feel free to type it in. I will answer them if you do have questions. And again, here we do see that our K value is small. So we are going to give it the old college try here and assume X is equal to 0. So again, it would be this X here. That will give us X squared divided by 0.01 equals 6.2 times 10 to the minus 10. We're going to multiply the 0.01 to the other side and also take the square root of it all in one move, hopefully. And this is going to get us an X value with a lot of zeros, 0.000000249. Again, we do want to check it to make sure our assumption is okay. So we're going to take that, we're going to divide it by 0.01, which is what we were going to subtract it from, times it by 100% to check it. And there, if we do that, it is nowhere even near 1%. It's like 0.02%, 0.02%, which means this assumption is good and we could keep it. Again, if you don't want to do the assumption, you can do the quadratic. You should get the same answer at the end if all the math is right. That looks like, since our H plus concentration does equal X, that looks like perhaps this number 2 here on the list would give us 2.5 times 10 to the minus 6 molar. It didn't ask for the pH in this case, but if you did the pH, it would give us something like a 5.60 in terms of the pH, which is again still acidic. So we would expect it to be acidic since it is an acid. And again, back to sort of that earlier question, you can see here we have a higher pH than we did say with that first weak acid at 0.5 molar. But remember, the concentration at 0.5 molar is going to allow a little bit more H plus to come off than here where we have a much smaller concentration to begin with. So we get a little bit higher of an acidic pH than we did with the other one based on the concentrations that we see. Any questions on this one here, or weak acids? Okay. Then let's talk a little bit about the idea of percent ionization and percent ionization. That was a good talk. Let's talk about basically what that is. So if we calculate the percent ionization of an acid, when we talk about an acid being ionized or an acid that is dissociation, going through dissociation, what we're talking about really is, for example, we are talking about really how much H plus comes off from the acid. So how much of the acid is basically heading in that direction. So to actually calculate the percent ionization of an acid, it's actually the exact same calculation that we do when we calculate our basically 5% rule. So we take the H plus concentration, which in our calculations before was essentially our X value, and we divide it by the initial concentration, which is essentially what we do, and we times it by 100%. And this gives you the percent ionization of an acid. Now, concentration has a big effect on, a weak acid in terms of, how much will be ionized, the percentage that will be ionized. When we have a strong acid, like we see here on this chart, a strong acid is, sorry, I didn't mean to X that out, will be 100% ionized, which means it's going to 100% drop apart into its ions. And that's why, again, it's a strong acid. It's able to generate H plus really quickly. But in a weak acid, there's an equilibrium that gets set up. So it's not able to generate as much ions as a strong acid, as you can see from the graph here. But what we do see from the graph is as the initial concentration gets larger, going in this direction of our weak acid, the percent ionization gets smaller. So as the concentration of our acid increases, the percent ionization, kind of decreases as well. And vice versa, if our initial concentration of our acid, which is what the little circle means, is relatively on the small side, the percent ionization goes up. And again, you could kind of think back to this as my classic pizza example, right? If you got a whole pizza here to start with, which would represent, a large concentration of an acid. And again, somebody just grabs the one piece out of there. That's not very much compared to the whole thing. But if you had just, bad drawing here, two pieces of pizza left, which would represent a small initial concentration, and somebody grabbed out that one piece, that is a bigger percentage, obviously, of what you started with than what you started with over here. So you lost a smaller percentage when you had more to begin with than obviously here when you had a smaller amount to begin with. If somebody takes one, then obviously you lost a bigger percentage. And that's what we see here. So if you have a larger concentration of a weak acid, when it breaks apart, the percent ionization will be relatively small. And that is also why, just to put it to numbers, when we did our 0.5 molar weak acid, the assumption was okay, right? The assumption was pretty much okay. But when we came to our guy that started with 0.05 molar, the assumption was bad. And that, again, is because the concentration was small to begin with. So when you lost a little bit of that small amount, that's a bigger, obviously, portion than when the concentration was larger and you lost a small amount. Any questions on that? So to sort of see how this will play out, let's take a look at this example together and kind of see what is going on here. So we're looking at a solution that is 8 molar formic acid, and it is 0.47% ionized. In this case, we actually want to calculate the Ka value. So they're not giving us the Ka value here, but you could kind of approach it like a normal problem. So we are looking for a Ka value. So that does tell us that this is a weak acid. So it is going to set up an equilibrium since we are looking for that Ka value. And it will break apart into H plus and HCOO minus. Our Ka expression in this case would be H plus times formate divided by HCOOH. We could even do our ice table here. We know we are starting with 8 molar of this guy, 0 this guy, 0 this guy. Change is going to be minus x plus x plus x, which means when we reach equilibrium, 8 minus x, x, and x. And normally what we would do is we would take this and put it into our equilibrium expression. The problem is we don't have that number, right? That is what we are trying to find here. So we need a way to figure out what x is in this case. And the way we could do that is with the other piece of information that's given to us. We know that this acid is 0.47% ionized. And percent ionization, as we just saw, is the concentration of H plus divided by the initial concentration times 100%. So really what we're looking for here is we need H plus, because H plus equals X in this case, right? So that is basically what H plus equals. So if we solve for H plus, we would have H plus equals the percent ionization times the initial concentration of our acid divided by 100%. And we do have all these numbers. So if we put it in, we have the percent ionization, which is 0.47%. We have our initial concentration, which is 8. And we have 100%. This is a long way to go to basically take 8% or 0.4% of 8. You move decimal place 2 places to the left to do that. But if we do it this way, we get something like the H plus concentration will equal 0.0376. And remember from our table, that is basically what X equals. And because that equals X, and when we look at our ice table, all the X's in our ice table are exactly the same. So this X here is exactly the same as this X and exactly the same as this X, which then means we already know all the answers here. So we can put the number in. That will give us 0.0376 squared divided by 8 minus 0.3, oops, keep missing those zeros today, 0.0376. And if we put those numbers in, we will get the Ka value, which in this case is it is 1.8. Let's write it this way. Let's around a little bit. 1.8 times 10 to the 1, 2, 3, 4. Looks like minus 4. So this is an example where you could actually use percent ionization and kind of work your way backwards. It's a very similar calculation to what you did or are currently doing in that equilibrium experiment where you do those ice tables and you figure out X and kind of work your way backwards. Any questions on that? Here we also see that the concentration plays a big effect in the percent ionization. We have a very high concentration of this weak acid to begin with. And that high concentration of the weak acid, which is 8 molar, when it breaks apart, is a very small amount, which is only 0.47% of it breaks apart. Any questions on any of those things? And this also, to tie it into an earlier question about, sort of that first one had a very small or low pH. If you calculate the pH for this one, is a pH of 1.42, which is really acidic, but it's still really acidic from a weak acid in this case. And it has a lot to do with, as you can see in this concentration, the concentration here is 8 molar. So because it started with more in terms of its concentration, when it loses that little bit, it's going to actually be a lot more H plus than, somebody that had 0.05 molar to begin with. Any questions on any of that there? Okay, couple of things. Let's see. Tuesday is our exam, so we're going to take the exam just like you took the quiz. It will be done on Canvas. We will have lecture on Tuesday just to try to keep on pace, and then after lecture, I don't know if we'll go the full time or not, but at least after lecture, during lab time, the exam will be open for you to go take it. Just like the quiz, there will be problems, obviously, where you'll have to show the work and then later upload it after you submit the quiz, the exam. And again, it will cover chapters 12 and 13. You will again have to obviously submit an answer online, and then obviously show your work with the answer and everything and upload it in a reasonable amount of time. So we'll probably do a lecture on Tuesday in the morning there, and we'll maybe stop a little bit early, give you a little break, and then the exam will be available for you to take maybe around 11:30ish when our lab normally starts. Give you that 3-hour window or so to sort of take it. Same thing like the quiz, you'll have a window opportunity to take the exam. Again, you want to make sure that you start well before the ending time of the exam. Otherwise, it will cut you off. So you want to make sure that you do that. In terms of the homework from the book, there will also be on Tuesday a assignment in the module section where you could upload the book homework that is due as well. There will be a time limit. I'm not sure yet. I'm still working on how much that will be, but there will be a time limit. Yeah. So you should have enough, hopefully, to do everything, I would think. So maybe somewhere between 135 minutes to 150 minutes. So, a couple hours or so, I think. You'll have probably a time limit to do the exam. I haven't fully decided yet until I kind of write the exam and kind of see what it would appropriately be. Yeah. Other questions on the exam or anything like that? Okay, so for lab today, again, what I'm going to do actually today is I'm going to actually continue lecturing in this chapter so we can hopefully get into some of the salts and those calculations and stuff like that to try to keep us on pace. So my plan is we'll take a little break here, maybe 15-20 minutes, and then I'll start up the lab meeting, and I'm going to continue lecturing at this point here, and I'm going to do some lecturing, probably not 3 hours of lecturing, but I'm going to do at least a good little chunk of lecturing to again try to keep us on pace, try to get us through the topics that you will need for the lab that we're supposed to start today, which is the pH of salt solutions and stuff like that. So my goal is to try to get through that stuff, and then after today, in terms of lab, later today or maybe tomorrow sometime, I will probably open up the next experiment, which is the pH one, and then obviously you could go off and sort of work on that. But I like to at least try to get through some of the material, obviously, that's covered on that. So we're getting very close to that. So I'm going to try to use today's lab period to do that. So for lab today, we will be continuing lecturing from this point in the notes, but we will be starting a new meeting. So that way the recordings will be separate, and I will obviously post up the recording for lab as well as this one. Any questions on any of that stuff? Okay, so let's take about a 15-20 minute break, and then we will gear back up and continue lecturing on this topics here in our notes for a little bit during lab. All right, if there's no other questions, I'm going to end this lecture meeting, and I'll see everybody in about 20 minutes.